Hello everyone. In this video lecture, I will talk about another spectroscopic technique. Here I will talk about EPR spectroscopy, that is electron paramagnetic resonance spectroscopy. Now, before coming to the definition and understanding of EPR spectroscopy, let us understand why it is important to understand EPR spectroscopy. Now, molecular EPR spectroscopy is a method to look at the structure and reactivity of the molecule. EPR is mainly limited to paramagnetic substrate. That means the molecular complex having an unpaired electron. When used to study of metal or protein, not whole the molecule is analyzed, but a small part of the prosthetic group where the paramagnetism is located, it is analyzed. This is usually the central place of the action, the active side of the enzyme catalysis process. EPR is highly sensitive process and sensitivity up to 10 micromolar and up. What information we get by the EPR? The spin state. The spin state of the metal, either it is diamagnetic or paramagnetic, the nature of the molecule, it is high spin or low spin or intermediate spin. Ligand environment. The ligand which associated with the metal center, their coordination number and geometry, types of ligand by understanding superhyperfine coupling, electronic state like d electronic configuration, exchange interaction between the metal center. It means that from EPR spectroscopy, we will understand this kind of thing: if spin state, ligand environment, electronic structure, d electron configuration, and the exchange interaction between the metal center means that coupling metal between metal and metal, the coupling constant. It's ferromagnetic or antiferromagnetic. The magnetic of the coupling J value we can get from the EPR. Now coming to the EPR spectroscopy definition and basic understanding of what is EPR spectroscopy. Now, EPR spectroscopy is a resonance technique involving microwave induced transition between the magnetic energy level of electron, which poses the net spin and orbital angular momentum. An EPR spectrum provides information about paramagnetic species. EPR spectroscopy, which is also called ESR spectroscopy, electron spin resonance spectroscopy, which is used to study paramagnetic species, paramagnetic sample having one or more unpaired electron. For example, free radicals, diradicals, metal complexes containing paramagnetic metal center. Also defects in semiconductors and irradiation effects in solids. While diamagnetic material are EPR silent, paramagnetic species always gives an EPR spectrum. This consists of one or more lines depending on the interaction between the unpaired electron and the molecular framework in which it is located. Analysis of the shape of the EPR spectrum that I will come to in the some later slide will gives the understanding by looking the position of the EPR line and their hyperfine splitting pattern, provides information about the paramagnetic species, that is the structure of the molecule, like it is free radical or the ligand environment, characterization of the coordination sphere around the metal center in the coordination complex, or the presence of multiple paramagnetic species. Now coming to the electronics of this EPR spectroscopy, first let us understand the Zeeman electronic effect. Let's take an example of titanium plus 3 or vanadium plus 4 metal center having one d electron, d1 system, titanium plus 3 or vanadium plus 4, or you can take copper plus 2 having d9 electron configuration with one unpaired electron. Now this kind of system have spin quantum number is equal to 1 by 2 half, and then therefore there are two possible orientation of spin state. One is image is equal to plus up, one is image is equal to minus up. So you can see this energy level diagram in presence of magnetic, in absence of magnetic field, where B0 is equal to 0, where the magnetic field is there is no magnetic field. The two level, that is image is equal to plus up minus up, they are degenerate. However, in presence of magnetic field, these two spin state, this energy level are splitted and giving this difference in the energy level. The lower energy is this image is equal to minus up, which is a beta spin state, and alpha spin state is designated image is equal to plus up. and the energy difference delta E between these two spin states are given by G mu beta into B naught. Now G is called Landis G factor, the G value. B0 is the applied magnetic field, which is normally represented in Tesla, and mu B is a constant term, which is Bohr magneton, and the value is given over here in joule per Tesla unit. Now this energy difference between these two spin states alpha and beta are corresponds to the microwave region of the electronic spectrum. That means if you provide suitable microwave radiation, the energy, when it will matches this delta E energy, the resonance will take place and molecule will give a EPR spectrum. So basically, so this splitting is actually called G-band electronic effect. So under the applied magnetic field, the interaction between this unpaired electron and this magnetic field, basically the interaction is between this electron and the magnetic field, resulting in the splitting of this energy level, and this is the called G-band electronic effect. Now for a free, now the G actually is a dimensionless quantity, and for a free electron this G value is normally 2.0023. For a metal ion, because of the spin orbit coupling, leads to the G value different uh, anisotropic features, which I will come at some later slide. Now coming to the one important part. Now the EPR spectroscopic measurement can be performed at a high temperature, room temperature, low temperature. Now the need for low temperature is very important to understand. The energy difference between these two energy level due to G-band splitting is very small, normal 0.3 centimeter inverse for X-band EPR spectrum. Now what is X-band? X-band is for where the magnetic field is 9.5 gigahertz. I'll come to that part later. I'll talk about different band of the EPR. So, so the two energy level, the alpha and beta spin state, because of this in a small energy difference at room temperature or higher temperature, the many of the molecule will be excited to promoted to the high energy state. So the population difference will be very less. So where N0 is the ground state population and N1 is the excited state population. So when this population difference will be small, the signal will be very poor. You will not get a good signal in the EPR spectroscopy. So in order to maintain the population difference, good high population difference to create a good signal, the need for low temperature is required. Now, if you look at this Boltzmann distribution formula, N1 is equal to N0 exponential to the power minus delta E by KT. So when you lower down the temperature, the this N1 by N0 value will automatically vary, will change. So basically when you lower down the temperature, by looking at this graph you will see that when you lower down the temperature from 100 Kelvin to like one to the gradual lowering the lower down the temperature, you will see that the N1 population, that is the excited state population, will gradually decrease, whereas the ground state population is gradually increase. That means that population difference will be very high at very low temperature. At low temperature it can be shown that only at low temperature there will be enough difference in the population, that is the number of electron will be in the ground state will be more compared to the excited state. So the S minus level, that is the ground level, N0 level, and S is equal to half 1 by 2 level, that is the N1, to create a signal. So basic understanding is that at low temperature there will be enough population difference to create a good signal in the EPR spectroscopy. So this is the basic fundamental understanding which can be understood by Boltzmann distribution, this formula. Now coming to the origin of this EPR spectra, how to analyze the EPR spectra. So first point is that the energy separation between the two energy level alpha and beta states correspond to the microwave region of the electronic spectrum. So thus by supplying appropriate microwave radiation to the sample, electron transition between the two energy level takes place. And then the system is in called resonance, and the recording of this transition represents the EPR spectrum. So this is like comparable with the NMR spectroscopy, where the radio frequency is provided in order to see the NMR transition. So, and another important point is that usually in EPR spectrometer operates with a constant radio frequency. So we had the radio frequency source is constant, which is normally in the 9.5 gigahertz for X band EPR. For other band like Q band, it is 35 gigahertz. Like S band, it is 2 to 4 gigahertz. L band, it is 1 to 2 gigahertz, and W band, which is 95 gigahertz. So the different band of EPR spectrometer. Normally, radio frequency like this band is fixed, constant, kept constant. Only the magnetic field, which is normally measured in Gauss or Tesla, is varied until the energy separation of these two spin states alpha and beta coincide or the matches with the micro radiation energy. So basically the two energy level alpha and beta for your sample molecule analyte, when it matches with the radio frequency of the X band spectrometer, that is 9.5 gigahertz, by varying the magnetic field strength, it will undergo in resonance and give a spectra. And how to look at the EPR spectra, that I will talk about here. The form in which an EPR spectrum is recorded is the fast derivative. This is the fast derivative. So in the blue line of the absorption spectra. So this red one is the absorption spectra. You see that this is absorption spectra. So normally the EPR spectrum is recorded is the first derivative of the absorption spectra. If you derivative the if you derivative with respect to the first order of this absorption peak, you will get this blue spectra, and this is how this EPR spectrum is shown. Because in this form, the detection is more sensitive and the signal to noise ratio is improved due to intrinsic electronic properties resulting from modulation of the magnetic field. So basically in the absorption peak, so this is very broad in nature, so you will not get many information regarding the peak. So however, when you derive first order derivative this signal, the signal to noise ratio is also getting decreased, and the exact position and the G value you can get. Now the point at which the derivative is curve is zero. So like this point where the point at which derivative curve is zero, that is crosses the baseline. So if you consider that this is the baseline, so if you so so if you consider that this is the baseline, so this point so this point where this derivative curve is zero, it is when it cuts that baseline. So and this point the magnetic field, and this point the magnetic field, which is referred to the B sample at this point, is recorded, and the G value for the sample is found out by substituting the value in the B sample. So basically you know that energy difference delta is equal to H nu G sample mu Bohr magneton and B sample. So when you know the B sample, how you know the B sample? So from the first order derivative graph, when the when the derivative curve is zero, that is it crosses the x-axis, the baseline, that point, from that point you will get that B sample. When you put the B sample mu Bohr magneton, that is constant, so H nu, you know that nu is the radio frequency for X band is 9.5 gigahertz. H is the Planck's constant. By substituting all the value, one can get the G of the sample G value. That is very informative, that is very important to know. By another way one can get the G value. So by taking the reference for old spectrometer or where the calibration is required, G sample can be found out by comparing the value of B sample with that of internal reference material for which G is already known. So this is actually internal sample diphenyl pigyl hydroxyl radical. This is the internal sample for which G value is known, fixed. G is equal to 2.0036. So basically you see that delta is equal to H nu, and for this molecule, for this for sample, and for this reference also, this H nu will be same. So you will if you and the mu Bohr magneton is constant for both the cases. So if you just equate these two equations, you will get this equation: G sample into B sample is equal to G reference into B reference. This is because you are having the same radio frequency, 9.5 gigahertz, H nu is constant. So this term G mu beta and B sample will be equal to that of reference also. So when you put these two in an equation, you will get that G sample. But you know the G reference, B reference, and B sample. So this G is, I have already told, is dimensionless. For free electron it is like 2.0023. For a metal ion, because of this coupling, spin orbit coupling, leads to the G value that are significantly different from that of free electron. Now coming to one or two important part, the G value obtained from this EPR experiment provides a diagnostic information about the system being investigated. For a paramagnetic metal center, G value is characteristic of the oxidation state, that is a number of unpaired electrons, and the coordination environment and molecular symmetry. So now there are three kind of EPR spectrum that are all not usually observed in the literature. So first one is the isotopic pattern. This is the isotopic pattern. For an isotopic system like MX6, where M is the metal ion, X is the ligand, with the octahedral geometries, the cuboidal symmetry. The three G value are equal to one another: GXX, GYY, and ZZ. So these are isotopic signal, isotopic pattern. So this isotopic pattern, so like tetrahedral, octahedral, icosahedral point group, so it belongs to isotopic. Now this G value depends on the orientation of the molecular principal axis. This is the principal axis of the molecule with respect to the magnetic field. So if the system is isotropic, like octahedral geometry, tetrahedral, icosahedral, this kind of cubic symmetry, if the molecule having this kind of cubic symmetry, then the EPR spectrum you will get isotropic signal shown in this blue line. This isotropic having one G value. This is basically the X, Y, Z three kind of direction is actually having same G value. So this is having G isotropic. For a system that is anisotropic, that means that uh, the principal molecular axis with respect to the magnetic field, it actually rotate molecule. So in that kind of system, it is called anisotropic, but has an axial symmetry and two axes x, y, and y that are equivalent, but are different from the principal axis z. So here gx, gy are same, which is called G parallel, and this gives rise to two values labeled G parallel and G perpendicular, that is z, depending on whether the molecular principal axis is located aligned or parallel to the magnetic field. So you can see that this kind of spectra is called axial spectra, axial kind of symmetry. This shown in the red color, axial symmetry, where one of the G is for G perpendicular and G parallel. G parallel is that of G value that which is parallel to the magnetic field orientation. This parallel means that direction, for example, Z axis is parallel to the magnetic field. So this is called G parallel. And G perpendicular here means that this X axis or Y axis which is perpendicular to the magnetic field orientation. So the G perpendicular and G parallel, it is for this axial symmetry kind of system. For rhombic system, so you will get three kind of G value, three types of G value: Gx, Gy, and Gz. This is also anisotropic system, and this is called rhombic type of EPR spectra. So there are three kind of spectra. One is isotropic, axial, and this is called rhombic. Now EPR spectrum of one line, as for a scalar gyromagnetic factor, is splitted, and the number of lines in the hyperfine pattern is given by 2ni plus 1 by this formula, where n is the number of equivalent nuclei with spin quantum number I. So let us see these two examples, then we will understand how we can calculate this hyperfine pattern, hyperfine line in the EPR spectrum. So this is the EPR spectrum of a cobalt 2 complex or cobalt is plus 2 oxidation state having one unpaired electron. So you can see that the interaction between this one unpaired electron resides on the cobalt metal center, which interacted with the nuclear spin of the cobalt 59 nucleus, having nuclear spin value I value is 7 by 2. Thereby, when you put this in this equation 2ni plus 1 formula, 2 into n, for n is 1 cobalt center, nuclear active, I value 7 by 2 plus 1, you will get this 8 line spectrum, give rise to this 8 line hyperfine splitting pattern for the EPR spectrum. So, and the midline, this 1 2 3 4 and this 1 2 3 4. So 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 the G value then will be calculated. So the G value will be this midpoint of this derivative peak. You will see that is shown over here, G value. From this point you will calculate the magnetic field strength, and when you put it in that equation you will get the G value, and the coupling constant on the this hyperfine coupling constant, that is A, which is equivalent to the inner coupling constant J also. That is the separation between this line, splitted line, which is designated as this capital A. Another example, this is the EPR spectra of a copper 2 complex, and now coupling between the unpaired electron resides on the copper 2. Copper 2 is D9 system having one unpaired electron. Now copper have two isotopes, 63 copper and 65 copper. Now natural abundance is given here, 69.2% for 63 copper and 30.8% for 65 copper respectively, both having nuclear spin 3 by 2. Now the unpaired electron of the copper plus 2, it will interact with the 63 copper giving this 4 line spectra, and the another isotope, it will interact with this unpaired electron giving this also 4 line spectra. So overall you will get a 2 superimposed 4 line spectrum. Here it can shown over here that this is a 4 line spectra because of the 2ni plus formula. 3 by 2 is a nuclear spin, you will get this kind of spectra, and this kind of splitting actually uh, the overlapping each for these two isotope actually, copper 63 copper and 65 copper. But you can see that A is the coupling constant for the 63 copper and A star is the coupling constant for the 65 copper. So naturally the higher molecular mass having this higher coupling constant, here you can see that 65 copper having the higher coupling constant compared to the 63 copper. However, the natural abundance of 63 copper is much higher. So here you will see that kind of 4 line, two superfine, actually two 4 line spectra which is superimposed on one another, and G value you can calculate from this midpoint of this 4 line. Then I have shown some example of super hyperfine coupling. So consider this example. This is the EPR spectrum of methyl radical CH3 dot. The unpaired electron over carbon due to the interaction with the 3 nuclear active hydrogen atom having nuclear spin is equal to 1 by 2. So if you put that in the 2ni plus 1 formula, 2 into n is equal to here 3 because of 3 hydrogen which is having nuclear spin 1 by 2. So into half plus 1 you will get this kind of 4 line spectrum having intensity 1:3:1 ratio following the Pascal triangle. So this is a quartet signal for the methyl radical, and this coupling is because of this unpaired electron of the carbon with the hydrogen 3 hydrogen nucleus. So this is the ESR spectrum of CH2OH radical. So you can see that this radical over carbon is coupled with these 2 hydrogen atom, and thereby giving rise to triplet spectrum 1:2:1 intensity ratio. And the and so this is another example of this ESS spectrum of this parabens semiquinone type parabens semiquinone anion, but you can see that there is one unpaired electron which is delocalized through all over this aromatic moiety, and there are 4 hydrogen atom which is nuclear active. So because of this 4 hydrogen atom having I value is equal to 1 by 2, it is having this kind of 5 line hyperfine splitted line quintet, and intensity ratio as follows the Pascal triangle. So those kind of hyperfine splitting due to the nuclear spin is equal to 1 by I is equal to 1 by 2, it will follow the Pascal triangle like similar in case of NMR spectrum. Here you can see that for quadruplet you will get 1 is to 3 is to 3 is to 1. For triplet you will get this 1 to 1 is 2 is to 1. Similarly for quintet you will get the same kind of pattern. So this is because of this spin coupling of this nucleus of hydrogen atom having spin value of I is equal to 1 by 2 with the unpaired electron of the of the overall complex molecule. These are few extra example uh, of the superhyperfine coupling. This is the EPR spectrum of this benzene anion. So you can see that there is paramagnetic molecule having 6 proton, and because of this 6 proton interacting with this one unpaired electron, you will giving this septate line, 7-line spectrum. This is the EPSR spectrum of cycloheptatrinyl radical, propyl radical basically. Because of the unpaired on of the unpaired electron is interacting with this 7 hydrogen atom, we will give this octet line, 8-line spectrum using the same formula 2ni plus 1 where n is 7 and I is equal to 1 by 2. This is the EPR spectrum of the cyclopentadienyl radical in a single crystal of cyclopentadiene at 170 Kelvin temperature. The radical is apparently rotating the molecule plane since all the protons appears to be equivalent. Because molecule are rapidly tumbling in the solution, all the protons are looking like equivalent. In all of this example I have shown over last 2 slides. So here you can see that the cyclopentadienyl and a radical anion, because of this 5 proton, they are exactly equivalent with respect to each other, and they are coupling with this unpaired electron, having giving this sextate signal, 6 signal, hyperfine signal. This is an example of metal complex, copper perchlorate complex, copper ClO4 whole 2, where copper is plus 2 having D9 electronic state, one unpaired electron is there. So if you look at the EPR spectrum, you will get a nice axial type of EPR spectrum. So from in the axial EPR spectrum, I have already told that there are two kind of G value. One is G parallel, one is G perpendicular. So basically G, this is the G parallel. This is basically G parallel line. This is basically G parallel, and G value is the midpoint of this line. This is the G parallel. This is G parallel, and this derivative part of this derivative peak, this is actually this is the G perpendicular. This is G perpendicular. So this is the copper 2 system having axial symmetry, or you can see that this is the G parallel and this is the G perpendicular line. And this kind of copper spectrum is very much important in biology because in the blue copper protein, and in order to understand different kind of copper environment, you have to look at this kind of spectroscopic parameter. So let's do this worked example and understand the EPR spectroscopy. The complex vanadial O acetyl acetone has a structure shown below. So this is the structure of this complex vanadium, this oxo bond vanadial double bond O, and this is the ligand part acetyl acetone. This is monoanionic ligand. So basically this is two monoanionic ligand, and this oxo, this is basically this is -2. So overall oxygen state of vanadium is +4 because -1 of this ligand, -1 from this ligand, and -2 for this oxo ligand moiety. So -4 for this ligand part, and so basically in order to maintain the electron neutrality, vanadium is +4 oxygen state. Now vanadium has two isotopes. The major is the 51 vanadium having nuclear spin is equal to 7 by 2. So the solution EPR spectrum at room temperature 29.8 Kelvin, the source it shows 8-line signal. So it's quite obvious because of this higher populated isotopic pattern. So you give this 7 by 2 split coupling with the nuclear spin and giving this 8-line spectrum. When the sample is frozen with liquid nitrogen, the EPR spectrum consists of two overlapping 8-line patterns, for which the G value are 1.985 and 1.942 respectively. Rationalize this data. So vanadium is in group 5, and the complex, the vanadium possesses +4 oxygen state. So therefore vanadium has one single unpaired electron. Now vanadium is almost monotopic. The pattern in the EPR spectrum is dominated by the hyperfine coupling between the unpaired electron and the vanadium 51 nucleus, which is the most abundant, having nuclear spin is equal to 7 by 2. Thereby, using the formula 2ni plus 1, 2 into 1 into 7 by 2 plus 1, you will get the 8-line pattern. So this is the EPR spectrum looks of this complex. You see that there is 8-line pattern because of this unpaired electron will interact with this vanadium nuclear spin and giving by this 8-line spectrum. Now, if you closely look at the molecule, it is not spherically symmetrical, but instead has an axial symmetry through the principal axis vanadium oxygen union. So basically, if you see, so there is a principal axis or C2 axis. You can see that through this vanadium oxygen bond. So if you rotate by this molecule by 120, there is a C2 axis is there. So it will overlap with each other. It will form the identical species. So the molecule is not overall symmetrical, spherical symmetrical, but instead has an axial symmetry. So at 298 Kelvin temperature, that is a room temperature, the EPR spectrum corresponds to an isotropic system. So this EPR spectrum is shown over here. This EPR spectrum basically is isotropic signal at 298 Kelvin temperature because the molecules are tumbling rapidly in the solution and an average orientation is observed. So because of this rapid motion in the solution, so average signal is observed because all these axes x, y, z axis are actually having the same value. They are actually experiencing the same value. So the average orientation is observed. However, on cooling to 77 Kelvin temperature, the spectrum splits into two superimposed 8-line pattern. These correspond to the principal axis of the molecule. One is aligning parallel to the magnetic field and one is perpendicular to magnetic field. And because of these two orientation, parallel and perpendicular with respect to the magnetic field of this kind of molecule at lower temperature, because at lower temperature molecule freezes, molecular motion gets slowed down. The two G value one will get. One is 1.985 and one is 1.94, which correspond to the G parallel. 1.985 which correspond to G parallel. That means that molecular axis is parallel to the magnetic field axis, that is the Z axis, and 1942 which is the G perpendicular, which means that molecular axis is perpendicular to that of Z axis, that is the magnetic field direction axis. Uh, Now the value 1.971, you can see that the G value basically at room temperature is in between these two values, G parallel and G perpendicular. Thank you. Now coming to the application of the EPR spectroscopy, that I have already told that in bioinorganic chemistry biology there are several metalloprotein are there which containing paramagnetic metal center like hemoglobin, myoglobin, blue copper protein. So in that case, in blue copper protein there is copper 2 copper 1 system is there. So by looking at the EPR spectrum, one can understand different form of this blue copper protein. Here I have shown this high spin system of this myoglobin, but you can see that there is G value at around 6.6, G is equal to 6 and G is equal to 2. This correspond to the iron 3 high spin state of this heme protein. So by looking at this kind of EPR spectrum of this biological molecule metalloprotein, one can understand the nature of the metal center, their spin state. Like here, the iron is present in high spin state because this high spin state having this characteristic diagnostic G value. One is around G is equal to 6 and G is equal to 2. And this is also an example of axial type of EPR spectrum. So this one is the G parallel and one is the G perpendicular. Thank you.